right. Good afternoon, everybody, and thank you so much for the kind invitation. Thanks a lot, Phil, for giving me the opportunity to talk to you here a little bit about what I've been doing in the last few years. Part of what I'm going to present here was things that I did during my PhD back in Germany, and some other things is some of the work that I've been doing since I've been in the CFA. So these are the names of some of my collaborators, and I will have so many things to tell you, so I will just go directly into it. So just before we start, a little bit on the motivation, and we want to understand kind of the environmental effects from the magnetic fields of stars. When I talk about environmental effects, I'm talking about all these things here: the high energy emission from the star coronal structure, the stellar wind, the interaction with the planetary magnetospheres, if they have some, transient events such as flares, coronal mass ejection, and all the way to the edges of the solar system, or the stellar system in this case, in the so-called astrospheres, the stellar equivalent of the heliosphere. To do that, we are actually trying to do kind of this between advanced observational techniques and simulations, try to get as much as we can from what people like you guys do in the solar system. There's an extra motivation for this, and it's bring it to us by the growing field of exoplanets. In the exoplanetary community, they are extremely keen to study and try to find planets around all sorts of stars. In particular, there's, well, there's now a big focus on, and one of the fundamental reasons is because those stars are extremely common in the galaxy. So here just I have a kind of an outdated picture. I think those percentages have actually grown for the M-class objects, where basically pretty much almost the entire population of stars in the galaxy are M-dwarfs. So the chances of finding planets there are just bigger. The key thing is that from the people that is studying the magnetic field of these objects, this represents kind of a challenge, because this region here, I'm showing you the mass of the star and the distance. This represents the so-called habitable zone, this range of distances in which a planet can sustain liquid boredom on its surface, provided sufficient atmospheric. To be a challenge for stars in this mass regime, just because of some of the magnetic and the stellar wind conditions that we will have there. And I will talk a little bit more about that in the rest of the talk. So the first part of this talk is going to be a little bit about detecting and mapping. Go quickly through this, and we can talk later. So basically, when we talk about magnetic fields in astrophysics, we need to talk about the Zeeman effect and the spectropolarimetry. So this is a little bit of history. Most of you here know much about this better. But the first measurements were done in the sunspot back in 1908 by George Ellery Hale. And basically what we have here is that the line splitting is going to be a function of the strength of the field, this parameter here that kind of encompasses the sensitivity of the line to the magnetic field, and it's going to be proportional to the wavelength of the spectral line square. So the redder you go, the to be to detect the splitting. And that the Zeeman effect introduces a particular signal in the polarization state of the components, and this will depend strongly on the geometry that you have and the position of the observer. So this is just a schematic view taken from Oleg Kochukov from winter school back in the Canary Islands. When you don't have a magnetic field, you have this simple relation, just a single transition, and when you turn on the magnetic field, you have the splitting, and one of the components has less energy, another one has more energy, and depending on the geometry of the situation, if you're looking at the same direction of the field, you will see these components in a circularly polarized fashion, and if you see it from a perpendicular direction, you will see it in a linearly polarized fashion. The bottom line of all of this is that if you're able to measure the splitting and the polarization of the line at the same time, in principle, you should be able to record vector property. And that is the whole kind of conversation about the spectropolarimetry. I don't expect to teach anybody here about this, because this is an institute of experts in the sun, but this is a little bit how, at least a little bit schematically, how it's done in the helioseismic and magnetic imager. They have an extremely well-characterized line, iron line, it's a highly magnetic sensitive line. And this line is characterized by different polarization and tuning filters in order to generate maps, polarization maps on the entire solar disk. And those are somehow inverse to retrieve what is the magnetic field in each one of the pixels. Those are called magnetograms, and they are of extremely high importance for understanding the sun and the environment of the sun, the stellar wind, and the conditions of Earth, and so on. So how do we do for other stars? So for this, we will go for high-resolution spectropolarimetry, and these are the main instruments that are used for this. There are more instruments now coming online, and there's a new one called Pepsi in an 8-meter class telescope that is going to, I think, revolutionize this field completely, because we're talking about larger apertures. You're going to reach much lower sensitivities and so on. But for the moment, I will just be focusing on talking about these three, which have been doing most of the work we have seen in the last few years: Narval at the TVL in France, Espadons at the CFHT in Hawaii, and the HARPS-POL at the ESO 3.6-meter telescope in La Silla in Chile. These are the spectral resolutions and the wavelength coverage of each one of them. And if you look at the relations that we just talked quickly before, you will notice that for the typical quantities, the signal from the Zeeman signature here is going to be below the sensitivity of this instrument. So what do we do for that? We have a solution, and that solution is a multi-line technique that basically what does is adds coherently the polarization signal in all the lines of the entire spectral range that you're covering. Since we have this very high resolution spectra, we can use tens of thousands and co-add coherently the signal from all of them. This is a technique called least squares deconvolution, although there are variations and there are different ways of doing it. I recommend especially this paper, the Kochukov et al. 2010, because it explores the limits and all the different details about the technique, if you're more interested in that. So the main idea, just a little bit quickly on this, is you're going to sum up over all the spectral lines, and you will have a weighted sum. And the weights for your sum are going to be given by the lambda factor of each line. It's going to be given by the wavelength, because as we saw before, the redder you go, the more easiest it's going to be to detect the splitting components, and the depth of the line, because the deepest the line is going to be easier to detect. So that is also taken into account when you are doing this weighted sum. One very important thing that has to be said here is, like, we are assuming here something that is called self-similarity, because we are assuming that the magnetic field distribution on the surface is totally unresolved, so it's going to be affecting all the lines in the same manner. So what we expect is that all the lines are going to have a similar shape, and this is what is called self-similarity. So those lines that are completely different one from another, they are removed and they are not included in the calculations of least squares deconvolution. And then this is basically can be written in the matrix form. And the idea of this matrix form is that you have this observed spectra, and you construct a very detailed line mask for your star. You have to know some of the properties of the star. And your idea is you are going to try to retrieve this mean profile, which is going to contain the entire polarization signature of the whole spectra. This is a matrix problem, and is solved in this way, taking into account the errors in each measurement. And the main idea is that you take the entire spectra with thousands of spectral lines, and you convolve it into a single average profile per observation. And the gain in signal-to-noise ratio is going to be proportional to the square root of the number of spectral lines that you're going to use in your mask.
You're mixing elements in that sense?
You're mixing elements, yeah. Yes. Yeah. So it's extremely average. So it's an average on absolutely everything you can think of. Of course, this is probably completely wrong for the people doing solar physics, but this is the only way we can reach the sensitivities to detect the fields at this moment. In extremely precise, for very nicely quality data, you can actually reach very high polarimetric sensitivity, but this is only in extreme cases. All right. So with that, this is how you detect the field. But now we're going to talk about how we map the field, how we convolve this information, a time series of these observations, into a 2D image of a map of what the magnetic field looks like. And this is done with the technique of Zeeman Doppler imaging, which is a derivation, a deviation from a technique called Doppler imaging, which was trying to map inhomogeneities in the surface of stars. But this one we will be talking about polarization sequences. And in one word, it's a tomographic inversion technique based on a time series of polarized radiation, which is modulated by the rotation of the star. So what you do is you go to the telescope, observe the star, go the next night, the star has rotated a little bit, you keep doing this, and you try to observe it as much as you can in phase with the rotation, and then you use all the spectral, those spectral lines that you have, and deconvolve the rotational signature to try to see what was the distribution, the 2D distribution that is able to reproduce all the observations at once. So when you do that, you require good phase coverage. You need to observe the star many times. You need to know some of the stellar parameters. You need to know the rotation period, for instance. This is something that is very important to plan your observations. It usually is only done with Stokes V, the circularly polarized light, because the Stokes Q signature, the linear polarization, is extremely weak in other stars. And when you're trying to get those measurements, it will mean that you will need to sacrifice at least half of your observing time to try to get the measurements in Stokes in linear polarized light. it assumes a static magnetic field. This is extremely important. It cannot resolve what is happening from the magnetic field from one observation to the next one. We simply don't have the resolution or the ways to do that. So basically, you assume that the large-scale field is not going to change much during one rotation, maybe two. Sometimes you can combine observations of two rotations, but not more than that, because you will lose the coherence. The magnetic field will really change. And then this is something that it will require a lot of time to talk about, but it will include a regularization function. And this is something that it will happen. It happens to every technique that tries to reconstruct some sort of an image from an incomplete data set, which is what we have here. And this happens as well, for instance, when you try to do interferometric observations. But I can talk a little bit more about that. Just in a sentence, this basically ensures that the solutions we have is unique, because you can actually have infinite magnetic field distribution that can reproduce your data. So you have to make some closure to the plot. The way it's done is with this regularization function. And at the end, what we recover is the large-scale field, kind of a large-scale vision of the magnetic field on the surface. These are called the ZDI maps. This is a little bit of the to the line core, because that is where the Doppler shift is minimum. You're close to the pole, you're not moving that much because of the rotation. But if this feature is traveling close to the equator, this particular bump is going to travel the entire line profile. So in this way, we can disentangle where in latitude the features are. And when you include the polarization information, you know that a radial field and an azimuthal field, for instance, something that is wrapping up the star, is going to introduce a very different signature in the Stokes V, for instance, the spectra. So this one will only grow bigger when it makes the transits, while in the azimuthal field, you will see a change of sign in the curve. And that this allows us to disentangle which components do you need to add to actually reproduce the entire set of observations. So some examples of this I'm going to present you here too quickly in the usual way as they are presented in the literature. This is in a Mercator projection, latitude, and this is phase, but this is longitude. And this is in a polar planar projection. And in here, you're looking at the pole of the star, and each one of these rings represents a 30 degrees in latitude. So the black line here is the stellar equator, basically. So you're seeing the star from the top, and it's flattened over a surface. And here, for instance, this is a sun-like star, Saibu A, fields on the order of 60 Gauss. And here, this is a M dwarf, and with a Bison of 5 kilometers per second, and you reach into the kilogauss fields for this one. This one is extremely dipolar field, as you can see, it's pretty much in the pole. And this one is much more complicated. It has this weird azimuthal band of magnetic field here. This is extremely strong, and we actually see this in many, many stars. So with this kind of information, this has been compiled kind of in this diagram, which is actually known as the confusiogram. So I will just try to break it down to see if at the end you get confused or not. So the symbol sizes represent the field strength. So the bigger the symbol, the stronger the field. So the sun is here. It's quite small. In the large-scale field, we consider that the sun has a large-scale field on the order of few Gauss, 3 Gauss, 5 Gauss maybe. And then if you stay at the same mass, this is stellar mass, this is rotation period. If you stay at the same mass as the sun, you will see that as soon as you go to shorter rotation periods, the symbols start to grow bigger. And this means that the fields become stronger. The color represents the main geometry. So if it's red, it's basically poloidal field. And if it's going to the blue, it's going to be like a toroidal wrapping up field. So like this one, this is the star I was showing you in the previous slide, Saibu A. And the shape of the symbol represents a little bit of the symmetry of the field. So if it's a decagonal shape, so the roundish shapes are going to be axisymmetric, while a star shape, like these ones, are going to be non-axisymmetric. So it's going to be much more complex fields. As you can see in the sun, for instance, in the case of a solar mass, you go to shorter rotation, the fields become larger, more complicated, and suddenly much less poloid and a little bit more contribution from these toroidal fields. So look at this regime here. We are talking here about the regimes of low mass stars, very low mass stars around the M dwarf regime, and you can see immediately the sizes of these things. So those large scale fields, we're talking about fields on the order of 2, 3, 4 kilogauss. And this will have extremely important consequences for what's happening with the space weather of those systems. So the conditions around those stars where all the exoplanet people are going to be looking for those planets. All right.
Is there any information on another axis, which would be inclination angle?
Do you really want to put another axis in that one?
But I'm wondering if there are certain stars you can point out that might be more polarized.
Right. I think you can do that, but I don't think has been done yet. I think there should be some information to try to disentangle kind of the biases because of this. Yes.
Is there a way to apply this technique to the sun? Do you have the information where you can?
There are efforts. There are efforts to try to do it, but unfortunately, none of them actually replicates exactly what we do for stellar observations. I think with Pepsi, it might be possible to do it because it's going to have extremely precise HL spectrograph with polarization capabilities, and you could, in principle, I don't know, make sun as a star fiber-fed observations and try to see if you can retrieve the polarization signatures in the same way. But so far, it hasn't been possible to do it. So right now, there are efforts trying to do it in only intensity. So try to do Doppler imaging, but you don't expect much of that out of the sun. But certainly, this is certainly that in the community, this is in the head of many people to try to see how the sun would look like under these conditions. Yeah. So I'm showing you here some of the examples of some of the stars I've worked on. This is part of what I did for my PhD thesis. This is a sun-like star, and this is the sequences of spectra that were acquired with HARPS. All of this is HARPS Pol in La Silla in Chile. And this is Epsilon Eridani, and this is another star. So here, for instance, you can see the impact from the quality of the data. You see the quality of this data is much worse than this one. And also the phase coverage, we have much less observations for this particular star. That means that the amount of details that you can recover in your map is going to be much limited here. So you basically just have a very broad picture of what might be happening here, and certainly you can retrieve more details in better sample and with more quality data. So that will be encoded, and that is a big complication when you try and compare maps of one star to another. Yes?
Is it typical that you're aiming for like a dozen different rotational phases? Is that enough to constrain the solution?
I would say that it would be, so the typical thing and a good case scenario, let's say we're talking about a star that rotates with a rotation period of 10 days. You will be good if you manage to get one observation for 10 consecutive nights. So basically, one observation every night. That is good. That would be a very good phase coverage, actually. I don't think you can do better than that. Maybe you can try, depending on your star, how bright it is and what is the signal-to-noise ratio that you need. You could actually try to get more observation during the same night. But I don't think that has been done for many stars because you probably know, but each Stokes V sequence requires 4 Stokes I sequences. So this is quite expensive on telescope to get just one of these. And then if you multiply this by maybe 2 per night, then your telescope time starts to grow, and then you just will spend all your time. So there's just a handful of those, actually. Yeah. But what happens is that usually you lose some nights due to weather, and then you will have to extend it for maybe 2 rotations. And this is what typically happens in most ZDI studies. Yeah. All right. So with this, I will now shift completely to try to use this information that we have retrieved using observations to study or to say something about the space weather sequence stars. And for this, we're going to use as much as possible tools that have been developed for our own. This comes hand by hand with the concept of data-driven numerical simulation that I'm pretty sure that people here are extremely familiarized with. We are using for this the so-called space weather modeling framework. This is a set of models that was developed by the University of Michigan that encompasses different domains in the solar system, from the corona of the sun to the solar wind. You can actually include planetary magnetospheres. There's different domains that you can couple in different codes, and is very well coded in such a way that it's not so difficult to actually work with it. So what you're seeing here, for instance, is comparison of synthetic images of the, synthetic images of the model's corona, which is driven by the Alphen wave solar model. The way that the corona is heated by is through Alphen waves. And this is the comparison with observations from different satellites, stereo A, and different wavelengths. So this is a high-performance, highly parallel code, so you need a cluster to do this. We have some computational resources to do this, and basically includes some of the physics we think is going on there, radiative cooling, electron heat conduction, and so on. One key important thing to mention is that one of the inputs for this is, in the case of the sun, is the distribution of the magnetic field on the solar surface. And this, in the case of the sun, is taken by the so-called Carrington maps, which is basically just an average field during one solar rotation. And this is more or less the same what we have in ZDI. So we have an average view of what the large-scale field is during one rotation. So what we're using actually as input, as driver for our simulations is the ZDI maps that we are retrieving from observations. And then you can actually model the corona, the winds, the environment, the star-planet, and so on. You name it, we can try to do it. So we have done certain experiments to deal with the extremely disparate differences in resolution that we have from the stellar observations compared to the solar observations. And we did this during the PhD to try to calibrate the models to be more applicable to stars, because we don't have the resolution that you guys have for solar observations. And you can actually simulate the coronal emission in different wavelengths and different, as it would have been observed by different instruments, because it was developed for the sun. So you have the response functions for different instruments, and yeah, I mean, the possibilities are very, very extended there. So what we have done this is what we understand that now that the coronal features of a star are going to be completely dominated by the topology of the field, while the conditions, the thermodynamic conditions, are going to be driven by the flux, by the unsigned flux on the surface. So this is done in a way that you compute your coronal model, and you can have a density and temperature structure all around the star in the three-dimensional domain. And then from there, you can actually calculate a three-dimensional emission measure distribution, which is only basically telling you how much of the material, of the coronal material, is at a given temperature in the corona. And from there, you can actually use this information to generate a synthetic spectrum of the star in the X-rays on the EUV that can be used to calibrate your synthetic images. And this is an extremely powerful procedure because some of these wavelengths are extremely difficult to access from the ground or from observations. So you can actually at least have a proxy of what the high energy radiation environment of the star is just from the models. So we can actually go even further away and try to simulate the winds of the star. So before doing any stars, we have to do the sun. And this is something that we did. This was published last year, 2 years ago. And we were doing these alpha wave simulations of the solar wind, and we get kind of this textbook picture of the solar wind during solar minimum, with the fast wind coming out of the poles represented by this shade here. The purple shade is this slow wind. As you can see here, this is a much larger simulation domain. So in this, we are building up this different domain when you have the star, and then you build up a bigger domain to include maybe planets or going all the way to astronomical unit sizes boxes. You have here the density structure of the equator, and you see the changes during the changes in the magnetic activity of the sun, and how it is dramatically imprinted in the structure of the wind. So our question is, can we do the same for stars? And this is exactly one of the things we did. So we have here one of the stars that I showed you before, from one of the stars that we managed to retrieve the Zeeman Doppler imaging information. And this is a similar picture. The colors represent the same, but as you can see here, the topology is completely different. In here, we have a slow wind coming out of the pole of the star, and we have fast wind closer to the equator. The density of the wind is a little bit higher than the solar wind density. And here, I'm showing you what is actually happening in the simulation. So inside this sphere, which is around 25 stellar radii, you have the star actually in the middle, and with the magnetic field imprinted of the observation. So the driver of this model is the ZDI map that we retrieve. And this surface here is the alpine surface of the solar wind, which is going to be extremely important when we talk a little bit about M dwarfs, because they are going to be facing a very strange regimes around those stars. And this is going to be important. This surface is important in order to calculate things like mass loss and angular momentum loss that are going to be extremely important for understanding the long-term evolution of these systems. And yes, I mean, we have Skomanish in this room, so this is like who actually studied how the stars were being slowed down by the winds and the angular momentum that they lose for this mechanism. So this is an extremely important calculation that we can do from our models. And then one of the neat things about this system is that actually you also have a planet around the system. And this is a particular interesting one because it's a Jupiter mass object in a highly eccentric orbit around only half an astronomical unit. And then what we did basically was just simulate, okay, let's see what happens if we put just a planet around this star. And then we just simulated there in two different conditions with a magnetosphere typical of Jupiter, let's say. And the interesting thing is that you can actually you can calculate the strong interaction between the wind and what would be developed as a bow shock there. And you can even go further and calculate the amount of radio emission that you will get from this interaction. And this is a quantity that's actually potentially detectable. So it's extremely high. It's 12 millijanskis during periastron passage. So we think that this is one of those systems that it will be possible to detect radio emission from the interaction of a magnetosphere, if the planet has one, with the stellar wind of the star. The only problem is that this system is located at -80 or something in declination. So there is no radio telescope right now that can look into this. But SKA will be able to. So we're waiting to see if our prediction is okay or not. I will now change a little bit to talk a little bit about the Trappist system, because this is a system that has given a lot of things to talk about. It's an M-dwarf star that has 7 planets very close in, with periods between 1.5 to 20 days. They are extremely packed around a very late M-type star, which is actually extremely active. So this is a little bit of the architecture of the system. So here we have the sun and the inner planets. Here, this is a block scale in orbital period in days. You have Jupiter here. How do you see the Galilean moons here, very close in? And this is how the Trappist one system looks like. All the planets are extremely close to the star. And these 3 planets, the planet, I think, C, D, E, are inside what is believed to be the habitable zone of the star. So that is why there's a huge buzz about them when they were discovered last year. So what we try to do, actually, this is work done by Cecilia Garrafo, one of another postdoc in the group that I am in the CFA. We don't have a SETI map available for Trappist, because Trappist is extremely faint. So with the current instrumentation, we cannot even detect the field. So what we did is we took a proxy star, one star that was similar in spectral type, similar in rotation period, and we expect for this to be a representative field. But this is a big caveat here, because we don't know exactly how the field looks like. For that star, this is how the field looks like. It's more like an inclined dipole of the order of 1.4 kilogauss. And then we did a simulation of the wind, and you have here the density, and this is the radial speed of the wind in a perpendicular plane. All these circles here represent the orbits of the planets, and the shade here is the alpine surface of the wind, the one that I was talking before. The first thing you need to know, and if you completely forget about the magnetic fields, is like because of the close distances, these planets are going to be experiencing densities that are orders of magnitude larger than the densities that the Earth experiences around the sun. So this will impose a really strong pressure on whatever structure of atmospheric structure that you have there. So you might think that, okay, maybe if the planets have some sort of magnetic shield like the Earth has, maybe they can survive. The real problem comes from the magnetic part of the story, because inside the alpine surface, some of the planets are actually inside completely. Even if you have a magnetosphere, what will happen is that the magnetic field of the planet will reconnect directly into the star. So you don't generate the conditions to form a bow shock and protect the planet. So the magnetic field of the planet will actually channel the particles into the planet, so it will make things worse. And if you think about the picture that I showed you with a confusiogram, all the M-dwarfs were looking at very big symbols there. So we're thinking that maybe all the M-dwarfs are going to have this very same problem, that this is something that was discussed by Ofer Cohen in his paper in 2014. So this is just something to think about for the habitability of M-dwarfs.
Can I just ask, you mentioned the inclination relative to what reference frame?
Which inclination?
The magnetic. You've got
Oh, this is just because we assume that the rotation axis is the Z axis in the simulation here, and then
that rotation axis, the rotation of the planetary disk.
For these planets, since, hey Charlie, they are extremely coplanar. I think the constraints are extremely good because all of them were transiting. So you expect that they are actually very close to the equator.
I'm just wondering why you chose that inclination.
Oh, this is because the proxy star, this is how the field of the proxy star looked like. Right. So that is the biggest uncertainty of this study. Of its own rotation axis, yes. Yeah.
That's a large-scale magnetic field of an M-dwarf rotating
at 1.4 days.
Axis there. How in heaven's name does that happen?
That's an extremely good question. Yeah. And you have to remember that, so here, there are some things that go into the technique, a lot of the details, but what happens is because of the regularization functions that we need to apply to retrieve the solution, one of these regularization is called the maximum entropy, right? So you are actually pushing your 2D distribution of the magnetic field into the simplest possible solution. And you cannot get a simplest solution other than a dipole, and maybe if you cannot fit the data, then the code will try to just basically find an inclination for it, right? So find another orientation so you can actually maybe fit the data. So again, it's all on the caveats of the technique because we simply have no way to go around that. And actually, this actually happens also when you're trying to do interferometric observations as well. You have to put some sort of regularization function to converge into a single final image that is able to reproduce all the phases that you have because your data set is by definition incomplete. So there are ways that this can be improved if we would be able to measure linear polarization as well, because that will give you extra constraints as well. But it's not possible yet. I mean, not with the current instrumentation. And especially MDORs are a little bit fainter. And right now, the instrumentation was tailored for the optical, but of course, they have much more stuff in the near infrared and stuff. So we might see changes in this in the near future because some of the spectrographs are shifting towards the near infrared because they're actually now trying to find planets around MDORs. But yeah, so this is a complicated question actually. Yeah. All right. I don't know how I'm doing in time here. Okay, so I will show you I'll try to make it quick, quick applications of what we are doing here to study a different kind of problem and in terms of active stars and what is called the suppression of coronal mass ejections in active stars. And I found this project extremely interesting. This is what I've been doing during the last year. And it's basically this idea of the connection that we observe in the sun about solar flares and CMEs. So I'm pretty sure that you guys here know, but when we're talking about flares, we're just referring about the radiation flash that occurs due to reconnection events. And when we refer to CMEs, we're more talking about the large amount of plasma that is released, this magnetized plasma that goes into the interplanetary space. So from statistics on the sun, we see that large flares most of the time come hand by hand with CME. So you get a large flare in the sun, and it's almost quite certain that you will get. Not always, but it's almost all the time. So the immediate question is, what happened in more active stars? Because those flares can be orders of magnitude larger than anything that we have observed in the sun, but also some of those stars are actually all the time flaring. So you see the light, they look like. So are they generating as? This is the fact that we have been looking for them to detect robustly a single stellar CME. And if this connection is true, then we should be seeing many of them. So what's happening? So one of the people that studied this, actually I think a postdoc here, Alicia Arnio, did a previous study, tried to estimate the contribution from CMEs to pre-main sequence stars. I'm going to be talking about a little bit more on the study from Jeremy in 2013, when he basically took the mass and kinetic energy relations that we observe for the sun in terms of the amount of X-ray that you see with the associated flare. And you see that he was able to manage to get these relations, these average relations for the sun. And you see that the larger flares, we generate more massive CMEs, and again the same, the larger flares will generate more energetic CMEs as well. So he explored the consequences of extrapolating this to the energy, to the activity levels that we observe in more active stars. And the conclusion was that you should expect a contributions from the CME to the mass loss rate around this number, 5 times to the 10 to the minus 10 solar masses. Energy requirement for sustaining this CME activity, this continuous CME activity, on the order of 10% of the volumetric luminosity of the star. If you have been following maybe the literature about these numbers are extremely large. So these numbers are extremely difficult to justify in any way from observations or what we have tried to estimate mass loss rates from stars, and from the kinetic energy requirements and the efficiency of a dynamo to generate all that many amounts of CMEs and reconnection events. So one of the conclusions of that paper was that these relations must flatten out for very large flares in such a way that you can generate the flares because we see them all the time, but you don't get the CMEs. So there has to be something happening. And the idea is that a possible solution for this is the suppression of CMEs by an overlying sufficiently strong magnetic field. This idea actually comes from solar observations. When you see active region like this one, this was a very big active region, I think one of the biggest in recent years. The active region, I don't know the phone number, 12192, I think, generated lots of X-ray flares. Here is the GOES class here. This is the X-ray line here. Many, many flares in the X-ray regime, many M-class flares, but from all of those, only one CME. And the idea was like this kind of dipolar configuration that you had here around the neutral line was actually serving like a cage, preventing the eruptions from going out. You generate the flares, but the plasma is not leaving. And this is the same idea we're trying to explore in stars. In stars, we know that large-scale fields in stars can be strong enough that they can provide conditions. And even if you go and look at dynamo simulation, this is work from Kesh Yadav, simulating a fully convective star with a dynamo mode, and he was getting kind of localized field pulse of this M dwarf on the order of something like 8 kilogauss. And there was a recent paper, I think, by Julián et al. Measuring these things, and he was getting numbers on the same order of magnitude. Kilogauss fields in fully convective stars. So the fields are there, so can they work as a suppression mechanism for the CMEs? So this is what we actually try to do using the set of models in the space modeling framework to simulate this kind of eruptions, the Gibson law flux rope CME model. We actually started eruptions in already a developed stellar wind, so our CMEs are actually going to flow in our solution. And we actually follow very closely what was done for the validation of this model in the solar case, because we don't want to simulate artificial things that have absolutely no connection to what we observe in the sun. So we follow very closely the solar CME study that was used to calibrate the model. This was done by Meng Jing et al. Last year, using this particular magnetogram and this particular active region here. So what we did was actually we just modified the magnetogram and we embedded it in a large-scale dipole of 75 Gauss. So we did this because of mostly computational requirements. So our cluster was not, let's say, powerful enough to simulate stronger fields, because those require much more computation time to calculate the wind solution, and then they evolve the time-dependent simulation for the CME to go off. This is just a little bit on the model. You can look into more of the details of this. We submitted this paper to APJ recently, just basically emulating what is done in solar observations, but with the difference that this star will have a large-scale magnetic field, a dipole field, that will actually try to prevent the CMEs from going out. We followed the CME evolution for 1 hour, and this is just quickly the results for this. So this, I'm showing you here what happened when the eruption goes. This is a kind of a relatively strong eruption in the case of the sun, and it's actually forced to follow the magnetic field lines of the dipole, and is not able to go even further away than a few solar stellar radii. It's just basically trapped there. We push the limits into the cold, and we actually get some CMEs managing going out. They highly compress the field as they move away, but they manage to escape the field. So these events, if we would have simulated these events in a typical solar wind configuration with a magnetic field of the sun, for instance, it will have reached speeds larger than 3,000 kilometers per second or more. But in our case, drastically reduced. The large-scale field drags it down, and it slows it very, very low speeds. This is very low speeds for the amount of mass and the kinetic energy of this CME. So with this, we actually run a bunch of models, and what I'm showing you here is the kinetic energy of the CME against let's say this is a quantity that quantifies how strong basically was the eruption that you put it in. This is a conversion that we can do to associate this with the energy of the associated flare that would have given rise to that CME. So we are talking here about the regimes of M, X, X10, X100, and X1000. So this is the range of energies that we're dealing here. And this is another conversion to total flare energies, because in stellar physics, you talk about total flare energies, not so much in GOES classes. And you see here that all of these events were confined. This line here is the mean behavior of the solar CME relation, where basically we observe that the kinetic energy of the CME is approximately 2 times the total energy of the flare. So this is this line, this dashed line here. This range here corresponds to the entire parameter space of solar CMEs. So in here we have all the way to X, I think X20, which is probably the largest flare that has been observed, and the largest kinetic energy for a CME. And what we show is basically that a 75 Gauss dipole is able to actually suppress pretty much all the CMEs we have ever observed in the sun. So only very strong events, these classical very large events like the Carrington flare and the 775 AD event that is kind of, is believed that happened, those two, it will probably be able to escape, but all the others probably would be suppressed. And this actually means that, oh, I'm sorry. Then this is a comparison with another study that actually Jeremy is doing, pursuing the same problem, but from a theoretical just kind of point of view, calculating this just from scaling relationships. He's not using simulations or whatsoever, but he basically has, same here, the threshold kinetic energy of the CME, and this is the dipole field strength of the star. So here we have the ranges of large-scale field that we, and here is the range of large-scale fields that we have for an active star. And these two works have been done in a completely separate way, but we are actually reaching the same conclusion. So basically, for a 75 Gauss dipole, you will only be able to escape, which is this regime above here. The kinetic energy of the CME is on the order of 10 to the 33 ergs, something like that. This means that the magnetic suppression will reduce the amount of CMEs that you get. You will mitigate pretty much all the small and moderate CMEs, and only the very big ones, monster CMEs, will be able to escape. And that could explain why we don't see them. And this is actually good news for the exoplanets, because if the star has a large-scale field, it will be preventing them for CME events from going. However, the light will go out. That is a whole other problem, right? The first will still go. We will actually try to observe signatures of this mechanism and explore what happens with the complexity of the large-scale field, because we only included a dipole because it's probably the most efficient configuration for confining the field. But we know from observations that the large-scale fields are much more complicated than just dipoles. So we can actually do that very easily in the code. This is something that Jeremy cannot do that easily in an analytical calculation. And then we are actually thinking that maybe there's some sort of connection between this mechanism suppressing CMEs and the appearance of superflares. So if this matter, this amount of plasma is not going anywhere, what's happening? It's going back, maybe colliding with the lower layers, and then maybe generating signatures that reach the levels observed in superflares. So this is kind of future work for us to do. All right. I don't know how much time I have. Okay. So I will now change completely again, and I'll be talking a little bit about changing space weather system. And this is going to be related with magnetic cycles, which I know some people here are working a lot on this topic. So we come back again to this plot, and there's one element that is missing here, and it's not the inclination field, but it's going to be time. And because we know time, because we know that these magnetic fields are not going to be static. They are going to be changing in timescales that are going to be comparable to the timescales that we know that the sun is changing in magnetic field, or even in shorter timescales. So we know this, of course, from solar observations. We know that the magnetic field of the sun is doing these beautiful patterns and this coming and going and doing this regeneration of the field and this whole field of study in the dynamo theory to try to explain this. Probably one of the most beautiful collages that I ever seen is this one in the solar cycle in the corona by Soho, the HST of solar physics, I would call it. And you just see how the corona lights up because of the magnetic field, and then basically shuts down and lights up again. So we know that the real reason behind all of these changes is what the magnetic field is doing, and one of the striking thing that it does is the changes of polarity of the field. So you have here positive polarity in the north, and then as the time evolves, there's all sorts of processes going here, and then you suddenly will reach the negative polarity in the northern pole, and this process will continue. But one of the interesting parts here is that the time scale for this to happen in the sun is about twice as long as the time scale for the activity to occur. So we are actually trying to see if we can actually see this in other stars. So people have done this since years ago, and there are experts in these rooms about this. Measuring the chromospheric activity in stars in the so-called measurement of the S index, which is basically trying to see this signature in the cores of the calcium HNK lines in the blue, very bluish region of the spectra. And when you compare it to a region when there are no activity, no faculae there, you will see basically no signature there. This was done for a classical paper in Sally Valley in 1995, and then they did it for a bunch of stars. Ricky has worked here a lot on this, try to identify the best stars with the cycles that are more closely resembling the solar one. But one thing that might be not known by many people, there are only 4 stars for which we know that, and they also show some sort of X-ray cyclic activity. And the reason I'm saying this is because when you look at the sun, the variability of the X-ray output through the solar cycle is 1 order of magnitude or more from minimum to maximum. So in principle, you should think like it might be easier to detect cycles in X-ray because the signature should be bigger. But unfortunately, we don't have dedicated telescopes for that. So actually, there are only 4 stars, and 3 of them are binaries. So if they are binaries, I don't even know what can be happening there. So I am going to tell you a little bit more about the remaining star that is there. And this star is a star that is very well known by Trappist here in the audience. It's Ionosphere. It's a sun-like star that has an age of 600, on the order of 600 million years old. And this is extremely interesting because this star is the youngest star where we have been able to detect some sort of cyclic activity. And the problem is like the younger the star, the more chaotic, let's say, the activity becomes, and then you don't see regular patterns anymore. So this is the youngest star we see this, and has a rotation period on the order of 7.78 days. And this is how the activity cycle looks like. So blue is the S index, the calcium measurements, and in red here, I'm showing you here, some of this data is not published, but this is data that has been acquired with XMM Newton by Jorge Sanz Forcada here, showing the X-ray cycle of the star. This is not a fit. This is just a sine curve with a period of 1.6 years. This is possibly one of the most beautiful X-ray cycles in stars I ever seen. So with this in mind, we actually started this very long campaign called the Far Beyond the Sun campaign that I started when I was doing my PhD. So we said, OK, I want to know what's happening with the magnetic field of this star. And so we have been submitting proposals to ESO since the period 96, it was late 2015, to try to observe the star as many times as we can each semester and retrieve Zeeman Doppler imaging maps out of it. So we have 3 maps per semester. We have been doing this since 5 semesters. We finished the 100 campaign here. I don't have the data reduced yet to show you here, but I will show you these 12 ZDI epochs that are already completed. Jorge, at the same time, was following it up with XMM Newton, and that is why we have this following this curve here in X-ray points. There are 2 more observations here that have been already acquired, but I think Jorge hasn't reduced them yet. And in the future, we're going to observe the star with HST, and we're going to try to observe it close to the minimum or the predicted minimum activity and to the predicted maximum activity. And this is going to be done in order to constrain better the coronal conditions and, more importantly, to try to see if we can actually get some estimates of the wind of the star. But I will tell you a little bit more about that at the end of the talk. So here what I did is I basically expanded this. This is from a recent paper that we published about this particular study. It was the first paper of the entire series of this study, when we actually did the analysis of the historical data for this, because there were some claims that the star had a very long cycle that for us were completely incompatible with what we were observing. So we analyzed all the information we had at hand, and we actually found that this behavior could be fitted by a superposition of these 2 periods. So we don't know if those periods are actually real activity periods or they're just a superposition that happens to be because of the geometry of the system. I think that is the case, but hopefully the combination of all the information that we have combined with Zeeman Doppler imaging, we will be able to tell like, these are not real activity periods, it's just the geometry of the system, and the real period of the star is 1.6 years as is indicated by the X-rays, which I think I trust more. One more thing important about this system is actually that the system has an exoplanet, and then it comes back again to the link with the people doing exoplanet studies. Jupiter, 2.5 Jupiter masses located at almost 1 astronomical unit, and depending who you ask, the planet will be completely inside the habitable zone or completely outside. So anyway, the important thing is, like, since we have extremely high quality data from HARPS, the spectrograph, remember that this is an instrument that was built to find planets, so it has an extremely high precision in the radial velocity. We also have this combined with all the activity and magnetic information. So in this particular paper, we analyzed that First, we wanted to see if we see the planet in our data, and that was the case. Actually, our RMS of our data was even lower than what the discovery paper they did before. But what we see here is that the activity actually determines a lot with what's happening with once you take the radial velocity signal of the exoplanet out, the residuals are actually dominated by the activity. It seems like there's a correlation. When you have higher activity, the residuals are higher, and we have lower activity, the residuals are below. To find more planets in this system, because the star has so much activity going on, you really need to first take care of this before trying to find another radial velocity signature there. But this is some of the things that you can actually try to do in a star that has a short cycle. We don't have this information. We don't even have it for. So, and I think this is extremely important because there's an increase in interest of trying to understand the activity of the stars as noise, because the people of the exoplanet community want to get rid of this noise. And this is a perfect system for trying to do that. So this is probably the whole point of that, and to try to see how the large-scale field looks like. So I will just move this here for a second. And then this is the same kind of plots that I was showing you before. This is just the radial field. Blue is coming inside the paper. Red is going outside. The scale here is 15 Gauss, and it's going to be changing in each one of the plots just for clarity to show some of the structure. So you maybe will get a little bit confused by the colors, but you make sure you look at the color on the numbers of the table. The line here is our estimation for the inclination. So from the V sin I, the rotation period, the estimation of the radius of the star, we believe that the inclination of the star is on the order of 50 to 60 degrees. So we don't see anything below this line. So when we started observing, there was this mixture of polarities here, and now I wouldn't be able to say which is dominating the pole of the star. In December, we saw this change already, and this is already changing in the field strength, but you could see that the pole was dominated by the negative polarity. We continue observing, and we see an increasing complexity. This is larger field strength. This is 50 Gauss. This is the largest, 55 Gauss. This is the largest we observed. This is February 2016. Even though, again, it looks darker here, it's actually weaker. This is only 12 Gauss. So the field becomes weak. It's basically the same here and the same here for these 3 months, 4 months. We continue our program. And here again, this is more or less the same scale. So actually, this is weaker, even weaker than before. And here we already see a mixture of things going on. I don't know exactly if you could think like, OK, maybe the positive polarity already is taking its place in the north pole of the star or what. But then we saw it. The next map. So this is February 2017. This is, again, a stronger field. This is 25 Gauss, the maximum strength. Again, even though it looks darker, it's weaker. But you can see it that in the last 3 epochs, it has been all the time in the changes in the magnetic field polarity and the magnetic cycle going on as what we were expecting. So from the prediction from this, we expect in this semester, we will actually retrieve again this polarity, completing the entire magnetic cycle.
So where did you see the inclination of this star?
So yeah, we are seeing like something like this, 60 degrees. So below 60 degrees, we see nothing. We see nothing. So we are seeing the pole. We're seeing it the whole time, basically. But yeah, exactly. And part of we never see it. So that's why you have this visibility limit here. So you don't retrieve anything there. So, and then with this information, you can go and bring up all your arsenal of models, all sorts of things. I'm just showing you here 2 possibilities. We're comparing the 2 times when we thought that it was the maximum in each polarity-dominated times of this cycle, and we make wind simulations out of it. So we can actually see what's happening with the stellar wind. It's the same kind of plots. This is the equatorial plane. This is particle density of the wind. The shades are the same as before. Green is fast wind. Purple is slow wind. And here I'm showing you here, these circles here of colors are actually the boundaries of the habitable zone of the star. So we can actually predict what are the wind conditions around the star in terms of the habitability. So we can predict, for instance, the pressure exerted by the stellar wind. So that can give you limits of what kind of magnetospheric protection you need to sustain an atmosphere in those conditions. And all of this is coming from observations as well. So what would be optimal is to tie this again 2 observations to see how good are our models compared to what we can observe in terms of winds of stars. And this is the next step of what we're trying to do. The thing is, mass loss and astrosphere, there are very few observational constraints. So we only know, or we have some sort of estimates of what is the mass loss of 10 sun-like stars. This is the plot. This is a plot taken from a paper from Brian Wood and others. Basically, what you're seeing here is the mass loss normalized by the surface area of the star in solar units. So our sun is here. And this axis is the amount of X-rays that you get flux. This is the X-ray flux in the surface. So basically, you have the sun here. And these measurements show this kind of connection between the more active the star, the more mass you're going to be losing, until a certain level, with what they call here the wind dividing line. And then you see that actually the mass loss becomes extremely weak. So the interpretation for this is a change in the topology maybe of the magnetic field. When you increase the amount of magnetic field, you can drive stronger winds, but at some point you have so much complexity and closed field lines that the wind is not able to escape anymore, and then you start decreasing again the mass loss. So, but this is all the observations we have. How are observations acquired? So this is done in the following way. This is kind of a cartoon. Basically, you have the sun, the entire solar system here in the heliosphere, and this is the interaction region between the heliosphere and the interstellar medium. And in there, you will form this hydrogen wall because of the presence of the solar wind, and it will become like this, this interaction, this shock region here, where basically the Voyager missions, there should be somewhere there. And you will expect that other stars will have similar because of their movement against the interstellar medium. So what these authors suggest, like you start with that intrinsic, sorry about this, because in this diagram, the sun is here and the star is here, and in this diagram, it's the other way around, but it doesn't matter. I will try to explain it quickly. So the star will generate this intrinsic Lyman alpha profile, and then once it crosses its own heliosphere or astrosphere in this case, it will get an absorption because of the hydrogen wall. It will travel through the interstellar medium and will get absorbed again because it has to cross the heliosphere of the sun. So in an observation, you will actually detect at the same time the astrosphere around the star in this kind of region here, this extra absorption in this wing of the line, and you will be detecting also the heliosphere of the sun. And this is the way they have actually estimated from the balance between the wind and the ISM what is the amount of mass that the star is losing through the wind. And this is the technique that has given us these measurements. So what we're trying to do in this proposal, actually, in the crossing the wind dividing line, is to see if we can get more data and to test some of our models. So we submitted a proposal to HST last cycle to observe these 4 stars. This is Ionosphere, the star that I've been spending too much time. To see if we can get measurements for this. The position of the stars here are actually coming from the mass loss of the models driven by ZDI observations. So these are data-driven calculations, basically. And we have these 4 stars here. One, Ionosphere is behind the wind dividing line, and the other ones are above. The thing is, our models cannot reproduce, for instance, this point here. We think there's something going on with these stars because those are binaries. So situation might be different there. You can have in a combined signature. There's lots of crazy things that can be going on in the binaries, but Epsilon Eridani is not a binary. But our models cannot reproduce this extremely high mass rate that they report. So we want to know if this is a particular situation for Epsilon Eridani. There's a problem with the technique. What else can be missing? Maybe there's an enhanced mass loss rate because of transient events like CMEs or something. Our predictions are actually much lower, so they're actually going through this direction. We can reproduce all this part of the diagram very well, including the sun. And these are our predictions. And additionally, we have here what we predict as a possible variability in this relation due to the magnetic cycle of the star, because the X-ray output is going to change because of the cycle. The sun does quite a change in this axis, not so much in this axis. And this is our prediction for Ionosphere, which is the only star for which we have that amount of information. And additionally, we requested time in XMM Newton because we need X-ray data for placing the x-axis of this diagram. But the observation for these 2 stars is extremely old. Many years ago, with cycle timescale, so maybe at the time we measure it with HST, it's going to be here, but the X-ray data is somewhere else. So we wanted to do it, with, let's say, kind of at least close to simultaneously. It's not possible to do it simultaneously, but at least, let's say, in a similar temporal time scale. So we can avoid a little bit of the variation due to cycles of variability in the X-rays. So I think I will end basically this very long talk. Hopefully nobody's sleeping. This is what we have in the present. So the high resolution spectropolarimetric door that enables us to do all this work. And this is what, again, the same instruments have been in the field. There are some others that are not become a very big player in this because of in the optical, I think, apart from how instruments are going to be changing in the future. So we will have an upgrade to Narval, thinking about radial velocity precisions for exoplanets, and it should happen this year. The espadonza, the CFHT, is going to be removed, and then SPIRU will take its place. And this one is actually, again, looking for planets around M dwarfs. But the interesting part about this one is that it will have a spectropolarimeter, and it will be always on, basically. So you will be trying to get radial velocity measurements of M dwarfs, but with the polarization measurements at the same time. So we will get lots of data for free, basically, for M dwarfs. This is particularly. And the same, again, this is Cryos Plus, an upgrade of this instrument. This instrument was placed at the very large telescope in ISO in Chile, in an 8-meter class telescope. Again, they are pushing the precision of the radial velocity, and it will be covering this spectral range, again, very low mass stars. But with an 8-meter class telescope, you can reach much deeper and go explore fainter objects. So I think that was pretty much everything I had to say today. Thank you so much for your attention.
We're running a little late, but we have time for a couple of questions. Tom.
You mentioned that you don't see CMEs around any of these stars. Why would you expect to see the CMEs around them?
Well, just by basically thinking of an extrapolation of the solar case, right? So when you see like an X-class flare, some studies say like there's a 90% chance, maybe 95% chance that that flare will generate a CME.
Observing that is difficult around the sun. It's
right.
Probably impossible around any distant star, but you said we don't see them.
Right, because people have been looking for them in other signatures, not like say directly resolve them, because there's no hope we can do that, but they're expecting to see, for instance, radio signatures of them, which should be extremely, let's say, peculiar. They should be easy to detect, and in the limits of current radio instrumentation, they should be visible.
The type 2 burst. Yeah.
And they don't see them anywhere. There are two events that actually caught the attention of some people, seeing these mega flares. There were insanely big flares in some stars. One of them occurred in Proxima Centauri, and another one was in Algol, the demon star. Those were extremely big flares, and those flares had an extremely strong X-ray signature, and while the flare was still going on, the counts were completely decreasing suddenly. And the explanation for this is like maybe there was a sufficiently dense material in between the line of sight that was actually blocking the X-rays, and this has been interpreted, maybe this was the filament going out, and then after sometimes you retrieve again the signature in X-ray. But this is the best we have right now. There are some other reports of strong Doppler shifts in things like H-alpha and other lines, but none of them is extremely convincing. I mean, the most convincing argument would be to see exactly a signature in radio, and we don't see them.
Interesting. One more quick comment. You mentioned habitability about CMEs. I don't think CMEs are going to be much of an influence on habitability. It's mostly the wind or atmospheric stripping and the proton radiation.
Right.
And proton radiation might also be trapped by these very strong fields, but it's probably going to have a better chance of getting out.
Yeah.
You could still have a very confined CME environment, but very irradiated.
Right. Yeah, that's absolutely true. Yeah.
And you see the type 3, because those are the electrons. That's why I would have thought even more than type 3. Type 3 radio.
One more, Travis.
Yeah, I just want to say great work on the time sequence of CDI maps for Ionosphere. I'm guessing you have, essentially you can use those same data to get the calcium HK index simultaneously
Yes.
to those observations. And those show the cycle continues, the short period cycles, or no?
So the calcium that I have for the not entirely, because so these cycle periods are right now on the same order of our time frame right now. So the analysis that we published was including the whole historical thing. We might try to redo it afterwards once we finish the 3 years of observations to see what we get. But again, we are at the limit of 3 years, and if it's 1.6, we only have maybe 1, maybe 2. But the calcium, what I can see, is doing crazy things in the star. And I don't know exactly what's going on because I am pretty sure that I have the best signal-to-noise ratios from the entire data set. But I see that it's basically, in some parts, it's actually not following the X-rays. And this is, I wasn't expecting that when I was writing the proposal. So my presentation card was like, look, this star is well behaved, the calcium is following the X-ray, this is what you guys published. It was very nice until that point, but after that, the star just went crazy, and I don't know. So we will see when we're done, yeah.
Okay, I think I'll stop the colloquium here, but he's going to be here for the rest of the day. I don't know what time you're leaving tomorrow.
It will be in the morning, but I will be here the entire rest of the afternoon if somebody wants to chat more or whatever. Yeah.
So you can do that. Or alternatively, I've been implored to announce that there is another colloquium today that might be interesting to some or all of you in the audience at NSO, which is by Adam Kowalski, who's been here as well to give a colloquium about why radio and submillimeter flares are interesting.
Oh,
so
sounds interesting.
that could be something to
Reviewing Meredith McGregor's paper.
Oh, okay.
If that makes a difference to anyone.
All right. Well, there you go.
All right.
Thanks.
Thank you.